Duct leakage.
The duct leakage procedures were taken from the Residential Reference Appendices section RA 3.1. These reference appendices can be found at the California Energy Commission's website at the link provided here, or you can download it from the Files section of the online training platform. The duct leakage test is used by installers and raters to verify that duct leakage meets the criteria for any sealed duct system specified in the compliance documents.
The overall training goal is to familiarize yourself with the duct leakage testing equipment, protocols, and forms. The point of this PowerPoint is to give you an overview and an eyes-on what the equipment is going to look like, the general procedures for the test, how to set up the equipment, and so forth. Once you're actually in your field training, then you will go through it in detail and actually setting up the equipment and yourself. It would be hard to learn this procedure without having the actual equipment, but at least by reviewing it step by step in the PowerPoint, you're then going to have something to reference back to once you actually get to your field training. These are the sections that we're going to cover in this PowerPoint. So we're going to go through the equipment specifications. So basically, there's specific equipment that you have to use for this test, and we're going to go through that in the following slides. So all pressure measurements shall be measured with an equipment having an accuracy equal to or better than plus or minus 1% of pressure reading, or plus or minus 0.2 pascals, whichever is greater. All pressure measurements within the duct system shall be made with static pressure probes such as a Dwyer A303 or equivalent. Now, you guys are not going to have to worry about verifying this information once you actually get your equipment. The equipment that's used in the industry on a nationwide level, it's very unique. There was only 2 companies that offered this equipment. However, if new equipment ever were to come on the marketplace, it's important for you to know the measurement specifications so that you can pick accordingly.
Duct leakage airflow measurements shall be measured with equipment that has an accuracy equal to or better than plus or minus 3% of reading, or plus or minus 1 CFM, whichever is greater. Now here on the left we have the 4 current versions of what we call a manometer, and that's what we call the pressure and airflow device. There's 2 manufacturers that make them, the Energy Conservatory, and those are the ones on the top, and then Retrotech has the ones on the bottom there. These are all the current versions of the meters. Energy Conservatory does have some older meters there, but this is likely what you're going to come across while out in the field. All instrumentation used for duct leakage diagnostic measurements shall be calibrated according to the manufacturer's calibration procedure to conform to the accuracy requirement specified in RA 3.1.2. Now, each manufacturer has different specifications for calibration. Some of them require yearly, others are on a 5-year cycle. So you do need to go to the manufacturer and calibrate based on their recommendations. Equipment for duct pressurization shall consist of a duct pressurization and flow measurement device meeting the specifications in section RA 3.1.2. So here on the right we have pictures of the 2 currently available what we call duct blasters. The top one's from the Energy Conservatory, and it is oftentimes referred to as a Minneapolis duct blaster. The one on the bottom is the Retrotech. Both of these come in kits. They'll include the fan, the duct work, the manometer, which is what we call the pressure and airflow measurement device, and a fan control to control the speed of the fan. So pretty much everything you need in order to perform a duct leakage test. So one of the methods that we use to measure duct leakage is called a duct leakage to outside test. And there is additional equipment that is required to perform this test. So in addition to the duct blaster, a duct leakage to outside shall include a fan that is capable of maintaining the pressure within the conditioned spaces in the house at 25 pascals relative to the outdoors. So this is what we call the blower door. And so there's two, again, Energy Conservatory and Retrotech. Both of them offer models that's a similar fan to the duct blaster, but it's just much larger. There's a frame, there's a shroud that goes over it, so it's going to be placed inside a door or window. And then you're going to use the same manometer as well as this, and then this one has its own fan control. So you're going to use this to adjust the pressure within the house to hit that 25 pascals relative to the outdoors, so that you can perform this duct leakage to outside test. And we'll go through the rest of the procedures for that test as we make our way through this presentation.
And finally, a smoke machine. The smoke machine shall be able to introduce controllable, non-toxic smoke. The means for generating smoke shall have sufficient capacity to ensure that any accessible leaks will emit visibly identifiable smoke. So the point of a smoke machine is if you're investigating the location or source of leakage within a duct system, you will be able to basically blow smoke into the system while pressurizing the ducts so that you can visually identify where the smoke is coming out of, hence identifying the leakage points in that system. And now we're going to talk about shortly about duct leakage and delivered BTUs and how duct leakage affects the efficiency of HVAC systems. So why is duct leakage important? Duct leakage reduces delivered BTUs and reduces system efficiencies. This translates into a higher energy use and a higher cost to the homeowner. The formula below is what we use to calculate delivered BTUs. It's 1.08 times CFMs times delta T equals the BTUs delivered. So 1.08 in that formula is a multiplier, and it's a constant. It will always be 1.08. The CFM is the delivered supply amount of air by the system. So this is the amount of air that's coming out of the supply side. The delta T is the difference, the dry bulb temperature difference between the supply and return temperatures. So like I mentioned in the building science portion of the training, the triangle means delta, which means difference. Delta T stands for difference in temperature, in this particular case, between the supply and the return temperatures. So in our first example, we're going to see an example of a system that has no leakage. We have 75 degrees interior temperature, and we have a system that operates 1000 CFMs. And because there is no leakage, you're going to have 1000 CFMs being pulled into the return and 1000 CFMs being supplied through the supply side. Now the delta T is 20 degrees. Please note that this temperature drop between supply and return is a default value for all systems. That is just an industry default. So the difference between supply and return is 20 degrees unless you know otherwise. But if we know that the interior temperature is 75, then with a 20 degree difference, the supply temperature will be 55. So if we plug in those numbers into our formula, you're going to have 1.08 times 1000, which is the amount of air being supplied, times 20, which is the delta T, which equals to 21,600 BTUs delivered. So our second example would be a supplied side leakage example, and let's see how that works out. So same house, we still have 75 degree interior temperature. It's still a 1000 CFM system. There's a delta T of 20 degrees. The only difference here is the fact that now on the supply side, instead of being 1000 being supplied into the house, you're losing 150 into the attic. So only 850 are supplied into the house, and you're losing 150 somewhere through the supply ducts in the attic. Now if we plug in the same numbers into the house, into the formula for the house, it's going to be 1.08 times 850, which is the actual supply CFM into the house, times 20, same delta T, equals 18,360 delivered BTUs. In the third example, we have return site leakage. So the only difference with this scenario is the fact that now we don't know the temperature on the return and supply side, because now we'll be sucking air from the attic. So we have 75 degree interior temperature and we have 135 degree attic temperature because it's a hot attic. So therefore the hot air into being sucked into the return plenum, it's going to affect the temperature of the actual air being introduced in the system. So we have 850 CFMs coming in from inside the house through the return grill, and then we have 150 CFMs being introduced from the attic through some kind of return leak into the system. So like I said, we don't know the actual temperatures because they will be affected by the temperature of the air leaking into the system from the return. So we have to figure those out. So if a 1000 CFM system is leaking 150 CFM, that equates to 15% of leakage. In this example, the system is pulling 15% of its nominal capacity from the attic. This leaves only 85% coming from the living space of the house, which is the actual return grill. We have to calculate the system temperatures based on the percentage of leakage being introduced into the system from the unconditioned space. And the leakage percentage will vary in every system. We're just using these numbers as an example. So how do we figure that out? So if you look on the right hand side of the instructions, so we said the 15% is coming from return leakage, 150 of 1000, that's 15%. So the decimal equivalent of 15% is 0.15. 85% is coming from the return of the house, that's 0.85, which is the decimal equivalent of 85%. We know we have 135 degrees of attic temperature, and we know we have 75 degrees of return or house temperature. So we're going to figure out what the percentage of each one of those degree differences are. So 0.15, 15%, times 135 degrees equal 20.25 degrees. We then multiply 0.85, which is 85%, times 75, which is the air from the inside of the house. So 0.85 times 75 degrees equals 63.75 degrees. You then add the two temperatures together. This is the estimated temperature at the return plenum. So 20.25 plus 63.75 equals 84 degrees, and that's going to be our return temperature. As we mentioned earlier, knowing that the default temperature drop between return and supply is always 20 degrees, by having determined the return temperature, we can now estimate the supply temperature. So 84 minus 20 equals 64, and that's going to be our supply temperature, 64 degrees. So now that we have our supply temperature, we can figure out delta T. So 75 minus 64, the difference between return and supply, is 11 degrees. So now we plug in those numbers in the formula. 1.08 times 1000, because there's still 1000 CFMs being introduced into the house, times 11, which is the delta T, equals 11,880 delivered BTUs. As you guys can see, the number gets lower and lower. So in our fourth example, you have return and supply side leakage. Same house, we still have a 1000 CFM system, we still have 75 degrees inside the house, and we still have 135 degree attic temperature. We're leaking 100 CFM return leakage and 200 CFM's supply leakage. So now, because we already have the delta T's in place, we're going to plug in those numbers into the formula. So you still have 1.08 times 800, because those are the supply CFMs. So you still have a 1000 CFM system that's leaking 200 CFMs into the attic. That means you're only supplying 800 into the house. So you have 800 supply leakage times the delta T, which is staying the same because the temperatures haven't changed. So with a delta T of 11 degrees, the delivered BTUs in this particular scenario are 9,504 BTUs. So in conclusion, a leaky system would only deliver a percentage of its system capacity, maximizing energy cost and decreasing the life of the unit. Because the unit will most likely run longer than it needs to, it will decrease the amount of time or the life expectancy of the unit itself. And these are our examples summarized. So example 1 was a no leakage system. It was delivering 100% of its capacity. Ideally, that's what we want. And it was delivering 21,600 BTUs. In example 2, we had a supply leak, and that resulted in an 85% capacity delivery, only delivering 18,360 BTUs. In example 3, because of the return leak, it was only delivering a 55% capacity because it brought the BTUs down to 11,880, being much lower. So you're about half of the capacity of the unit. And then in example 4, where you had both supply and return leaks, it only delivered 9,504 BTUs, being approximately 44% capacity. So you guys can see where the problems lie when it comes to duct leakage. Now, where does duct leakage come from anyway? And these are just some of the most common examples that you'll see. So on the left-hand side, you'll see improperly sealed duct connections. So anywhere where there is a connection of a duct to another duct, or maybe a plenum or a junction box, there's the potential that it's not going to be connected properly and there's going to be leaks. So if improperly sealed duct connections, we'll see a good amount of leakage in the overall size of the system. In the middle picture, gaps between register boots and drywall should be sealed. In this particular picture, they're not. So if they don't stay sealed, whether it's a return grill or a supply grill and register, it doesn't matter. If it's a return register, then and those edges are not sealed, the return will then pull air from the subfloor or from within the building cavity rather than the house. If it's a supply register, then the supply register will push air into the building cavity rather than into the house. So the gaps between the register boots and the drywall have to be sealed. And then last, unsealed penetrations in the cooling coil. So any kind of penetration within the cooling coil casing has to be sealed somehow. If not, you're going to get supply air escaping from it. So it's important that those particular penetration points are sealed. Now, there's plenty more areas where the system could be leaking from, but these are by far some of the most common. Once you actually get in your field training, you're going to be working with a live system working in an actual house, and you'll be able to identify many more areas where leakage could be coming from. Now we're going to be talking about determining nominal airflow for the system.
In order to determine the allowed duct leakage, you must first determine the system airflow. This can be done by one of three possible means. The first one is default air handler airflow, second is the nominal air handler airflow, and third, the measured system airflow. Airflow is always going to be measured in CFM. So the first option, and most likely the least used, is going to be the default air handler airflow. This is to be used only for homes where the duct system is being tested before the air conditioning and heating system is installed and the equipment specification is not known. If you know the size of the heating and cooling equipment, you cannot use this method, which is why it's not going to be used very often. If it is a heating only system, the default air handler airflow shall be 0.5 CFM per square foot of conditioned floor area. The nominal air handler airflow can be calculated in one of two ways. It's either going to be, if you're using the heating method, you're going to do 21.7 times the kBTU per hour of rated heating output capacity. Now don't get this confused with the input capacity. A lot of furnaces will list the input capacity but not the output. So you need to make sure that you're using the output capacity on those. Or if you're going to use the cooling method, it's going to be 400 CFM per ton of condensing unit size. So it's going to be the tonnage of the unit, and those are usually somewhere between 1 and 5. And that's for a standard duct system. If you're using a small duct high velocity system, it's going to be 250 CFM per ton of the condensing unit. Now you're going to use between which do I use, heating or cooling? You're going to use whichever method gives you the greater airflow, which will make it easier for the duct leakage test to pass. Most often that's going to be the cooling method, but every now and then the heating method will provide a greater airflow target to use. If you're using a heating only system, you must use the heating method because there's no condensing unit to get the tonnage from to use the cooling method. So yeah, most often you're going to use cooling method, and it's going to be 400 CFM per ton to get that nominal air handler airflow. But every now and then you're going to be using that heating method, and even more rarely, there's not a whole lot of small duct high velocity systems out there, but you may come across those at some point during your inspections.
So here's an example for the heating method. The furnace has 80,000 BTUs of output. So the kBTUs for 80,000 would be just 80. So 80,000 BTUs equals 80 kBTUs. So the formula is 21.7 times the kBTU of output capacity. So that's 21.7 times 80. So the nominal airflow for that particular unit is 1736, 1,736 CFM. Keep in mind, airflow is always measured in CFM. The cooling method for the same scenario, that particular system has a condenser that's rated for 4 tons of cooling. So the formula is 400 times the tons of cooling capacity, 400 times 4, that gives us a nominal airflow of 1600 CFMs.
Now the calculation for a small duct high velocity system is going to be very similar to that cooling. We have the same 4 tons of cooling on this one, but we're going to be 250 per ton instead of 400. So we'll do 250 times 4, and that's going to give us an airflow of 1000 CFM. And the last method is the measured system airflow. So this one can be used anytime you can actually measure the airflow of the system with one of the devices that we'll talk about in a little bit later in the adequate airflow section. So the airflow will be measured with those same procedures that you'll be using for adequate airflow, and that's found in RA 3.3.4. The airflow will be the actual CFM measurement that's recorded when conducting that procedure. And again, we will be covering that later in detail, the different types of equipment that you can use, as well as how you will collect that data.
Now we're going to be covering the actual procedures on what to do with the duct blaster fan and how to hook it up. So the test protocol you need to use are determined by the situation that you're in. And there's also different test criteria and thresholds based on the scope of work you're conducting, and they're outlined in table RA 3.1-2 of the residential appendices.
So here is table RA 3.1-2. There's actually going to be two, it's broken up into two pieces, so we'll look at the second half of it on the next slide. But what this does is it breaks down the verification description, the user application, and then which procedure within the reference appendices you would use in order to complete that verification. So this breaks it down for new systems that are in townhomes or single-family homes, and whether the installer is testing at final or at rough-in, or is it multifamily, or it just breaks down these different scenarios and then references the reference appendices as to which is the appropriate procedure to follow for that particular description. And so here's the second half of that same table. It's laid out exactly the same, and you can see on this one here, the first one had a lot of new systems, where this one we can see we have several examples for sealed and tested altered existing duct systems. And again, depending on how if the installer's doing testing or the HER's doing testing, and how that goes, which procedures within the reference appendices you're going to need to follow in order to perform that verification. Along with those different procedures, there's also different what we call pass criteria. So when we perform this duct leakage, we're looking for the amount of leakage that is a % of the nominal air handler airflow. So we've already figured out how to calculate that nominal air handler airflow, and then what we're going to do is we're going to take a percentage of that, and that's what we're going to try and be equal to or less than when we perform our duct leakage test. So these different types of systems are going to have different percentage values that we need to try and achieve. So for an entirely new or complete replacement duct system in a single family dwelling, it's going to be 5% total leakage. For that same system in a multifamily dwelling, it's going to be 12% total leakage. For an entirely new or complete replacement duct system in multifamily, you can also do, or you'll be doing 6% leakage to outside. And remember, we talked about total leakage versus leakage to outside, and we'll cover those in more detail here in a little bit. If we have a new system and the HVAC contractor is testing at rough-in with the air handler installed, again, this is for the CF2R only, which is the contractor only. This is not the HERS rater verification. They'll be testing at 5% total leakage. If it does not have the air handler, they can test at 4%. Again, contractor only. If they take a credit for low leakage ducts in conditioned space, that's on the performance side. On a single family, we're not going to be doing a percentage. We're going to go to a straight 25 CFM leakage to outside. So again, we'll be doing the leakage to outside test, and it has to be equal to or less than that 25 CFM value. For an altered duct system in either single or multifamily, we have two different options. You can either do a 15% total leakage or a 10% leakage to outside. If you can't pass either of those, then there is what we call the smoke test option, but that's only after you were not able to achieve a 15% total or 10% leakage to outside. You'll simply will smoke the system with that smoke machine we described earlier, and you won't be able to have any visible smoke. So any leakage would have to occur in inaccessible locations, and again, we'll cover that in a little more detail. For altered ducts and duct system components in garage spaces, for single family, it can be no more than 6% total leakage. And then again, if you can't achieve that, then we go back to that smoke test, and you can't have any visible smoke in those accessible locations. If the performance method was used, this is where you will find the duct leakage target on the CF1R. So on the CF1R PDF, you'll want to scroll down until you get to the HVAC distribution HERS verification section. There in column number 3, you will find your duct leakage target in a percentage, and you can see in this example here, a 4% leakage rate is what was modeled. So that's what you will need to test for. You need to be equal to or less than that value in order for this to be a pass. So as you can see based on that list, there are two ways or two methods that you can use to test a duct system. There's the total duct leakage, and there's the duct leakage to the outside. Now these can be, the total duct leakage is going to be represented as a percentage of some value, which is going to be the nominal airflow. Duct leakage to outside, when you perform that test, you could also, sometimes they'll use a percentage, but also you will see that it is possibly a static value. For example, with the ducts in conditioned space, it's just a static 25 CFM leakage to the outside. So be sure to keep that straight, whether you're using a static target or a percentage. So let's go through. Let's start with total duct leakage. That is going to be the primary method that you will be using for your duct leakage verifications. And then we'll also get into a duct leakage to outside, and then we'll follow that with alterations. Alterations going to use the same methods, just different targets, with the exception of the smoke test, but we'll cover those all next. So let's get into total duct leakage.
Total duct leakage is determined by pressurizing the entire duct system to a positive pressure of 25 pascals with respect to the outside. And the following procedure shall be used for the fan pressurization tests. So total duct leakage, you're basically hooking up the duct blaster to the air conditioning system and pressurizing the system to 25 pascals. When we say pressurizing, you're basically pumping air into the system. So the first step is to visually verify that the air handler, supply and return plenums, all the connectors, transition pieces, duct boots, and registers are installed and sealed. The entire duct system shall be included in the total leakage test. You cannot portion off portions of the system, so it has to be tested as a whole. There is no temporary taping allowed, for example, of fresh air vents or dampers or so forth. However, motorized dampers can be set to the closed position during testing. So ultimately, the system must be tested in its normal operating condition, however it is that the system is going to be once the homeowner is actually using it. You have to visually verify that cloth-backed rubber adhesive duct tape has not been used. If it has been used, it was covered with mastic and drawbands. Building cavities are not being used as ducts, for example, belly cavity returns or chases in the walls. And then all supply and return register boots have to be sealed through drywall. Please keep in mind that even if the leakage percentage is below the thresholds that you're supposed to meet, failing these items constitutes a fail in the actual test itself. So these items have to be installed properly, have to be visually verified for the test to pass. Next, you're going to see all the supply registers and return grills except for one large centrally located return grill on the air handler cabinet and access panel. When you're sealing the registers, make sure that you're sealing the tape to the surrounding material, meaning the drywall or the wall, and not the register itself. If you don't, then there is a chance that air might escape through the sides of the register grill through the seams. So therefore, you want that tape to be all around the actual seam itself to the drywall and not just the metal of the register. So yeah, you're going to seal all supply and return registers. If there's multiple returns, you want to seal all the secondary returns, and you're going to be using the main return to hook up your duct blaster into in the next step. So you're going to remove the filter from the return that you chose to use as required by the manufacturer's instructions. And then you're going to attach the fan flow meter or the duct blast duct to the duct systems at the unsealed return grill or the air handler cabinet access panel, however it is that you're choosing to do it. You then are going to install a static pressure probe at a supply register located close to the air handler or the supply plenum. You will go to your duct blaster and you will set the appropriate ring on the duct blaster based on the manufacturer's specifications. Ring size will affect the airflow being pushed through the system, and please refer to the equipment guides for ring selection. If you look in the back of the Cheers manual, the equipment guides will have information about ring selection, and again, once you actually do it hands-on in the field test, you'll get additional practice and experience with that. Again, here in this PowerPoint, we're just letting you know what you're supposed to do as far as the steps so that you'll be able to recognize what to do during the actual field training. Then you're going to set up your manometer, and again, you'll be setting up your manometer hands-on during field training. And you're going to pressurize the ducts to 25 pascals with respect to the outside or with respect to the building space where the entry door opens to the outside. So once you pressurize the system to 25 pascals, you're going to be reading a CFM flow reading from the manometer itself. So you're going to record the flow through the flow meter, and that is your leakage flow at 25 pascals. That is the amount of air that the system is leaking at 25 pascals of pressure. Now keep in mind, pressure is always measured in pascals, flow is always measured as CFMs. So once you take the measure of flow reading, you're going to divide it by the nominal or system airflow determined previously. You're going to convert that to a percentage.
So now to calculate that leakage percentage, we're going to take the measured flow, which was the CFM value that we took off of the manometer during the duct test itself, and we're going to divide that by the nominal or system airflow, depending on which method you use to calculate your airflow, which was either heating, cooling, or measured. So we're going to say that we had a measurement off of the manometer of 80 CFM, so the duct system is leaking 80 CFM of air through it. We're going to divide that by 1600 CFM, which we got from using the cooling method. The 400 CFM times 4 tons was 1600 CFM. So 80 divided by 1600 is going to equal 0.05. We're then going to need to convert that to a percentage. So we do that by multiplying it by 100. So 0.05 times 100 equals 5%. You're now going to take this 5% and you're going to compare it against the required value. And again, it's going to range anywhere from 4% up to 15%, depending on which type of system it is. So you're going to compare that. If this was, say, for example, a newly installed system, that would be a 5% target. And so this would pass at that 5% leakage rate. If the leakage flow percentage is equal to or less than the compliance criterion from table RA 3.1-2, then the system passes.
Now another way to conduct duct leakage testing is duct leakage to outside, or LTO for leakage to outside. You might hear referred to it as that sometimes. So the objective of this test is to determine the amount of duct leakage to outside the air barrier for the conditioned space. This measurement is utilized to verify the duct systems are located entirely within the conditioned space. The duct leakage to outside shall be determined by pressurizing the ducts and the conditioned space of the house to 25 pascals with respect to the outside. And the following procedure shall be used for the fan pressurization test of leakage to outside. So for this particular test, you'll need a blower door and a duct blaster because you'll be pressurizing the ducts to 25 pascals, plus you'll be pressurizing the house to 25 pascals as well with the blower door. So first of all, you're going to set up the duct blaster as previously described, same exact way.
Next, you're going to attach a blower door to an external doorway such that it can pressurize the home. So you want to have the fan facing inward so that you can pressurize the house to 25 pascals versus when you're doing a blower door, you're generally going to depressurize the house. So this is going to be set up in the reverse of what you would normally do for a blower door test.
If any ducts are located in an unconditioned basement, all doors or accesses between the conditioned space and the basement shall be closed, and at least one operable door or window, if it exists, between the basement and the outside shall be open during the test. If the ducts are located in a conditioned basement, any door between the basement and the remaining conditioned space shall be open, and any basement doors or windows to outside must be closed during the test.
So next you're going to turn on that blower door fan and you're going to adjust it to where it is providing a positive 25 pascal pressure in the conditioned space, and this is with respect to the outside. So this is again the opposite of what we normally do for the blower door test, which is we turn the fan on and we try to achieve a negative 50 pascals. In this condition, we're trying to create a positive 25 pascal in that conditioned space with respect to the outside.
Then you're going to adjust the fan flow meter, which is basically the duct blaster, to maintain a zero pressure difference, plus or minus 0.5 pascals, between the ducts and the conditioned space. So you will adjust the duct blast manometer until the pascal reading says 0. So you're going to crank it up until the pressure is equalized and the pressure reading on the duct blaster manometer says 0.
You will then record the flow through the fan flow meter, and this is going to be the duct leakage flow to outside at 25 pascals. So on your manometer, you're going to have the 0 pascal pressure on one side, and then you're going to have a leakage flow in CFM on the other. That is what you want to record. Now, if that leakage flow is less than or equal to the applicable compliance criteria in table RA 3.1-2, then the system passes. Now, generally this test is going to be used for when they take the credit for ducts in conditioned space, and that's going to have a static target of 25 CFM. So it's not going to be a calculation to a percentage. It's going to be if it is less than 25 CFM leakage to outside, then it's a pass. But again, you'll want to go to that table to verify which criteria you need to use. Now, if the compliance does require you to convert it to a percentage for the pass-fail criteria, you can still divide the leakage from the fan flow meter by the nominal or system airflow that we determined earlier and convert it to a percentage as previously described. Now, if that leakage flow percentage is less than or equal to the criterion from table 3.1-2, the system will pass.
Keep in mind that with the duct leakage to outside, the same visual verifications apply as explained before in the total duct leakage section. So even though the test method changes, these visual verifications don't, and they still have to be applied. For HVAC changeouts, the standards make a distinction between two types of HVAC changeout situations. You have entirely new or complete replacement space conditioning systems, or you have altered space conditioning systems, and the standards do vary from one to the other. For the first scenario, entirely new or complete replacement space conditioning system, what does that mean? This is the definition of what that actually means. So it must have all heating and cooling equipment new. The duct system meets the definition of an entirely new or complete replacement duct system, including system with less than 40 feet in length, and that is at least 75% of the duct material is new, and any remaining component from the previous system are accessible and can be sealed. If those items are all true, then this system is considered an entirely new or complete replacement space conditioning system. Now, keep in mind that even though the system could be new, doesn't mean the house has to. This could be a scenario where you have an old home that has 100% of the system ripped out of the old system and then replaced with a new one, or a house that never had a system and a system was added. So those scenarios will still fall under this category.
So it must meet the mandatory and prescriptive requirements for new HVAC systems as previously described. So back in the Title 24 overview, we kind of went through those different ones. So potential for, depending on the type of alteration that's done, it could be duct leakage testing, fan wash draw, airflow, return duct design, and air filter design. Prescriptive side, refrigerant charge. So there is the potential for several HERS inspections to be required, along with the mandatory measures for equipment efficiencies, duct R values. All those items do come into play on these systems. Now for an altered space conditioning system, any of the following items here will be considered an altered system, and it shall be tested as previously described. So if an air handler, an outdoor condensing unit of a split system air conditioner, or a heat pump is installed or replaced. Number 2, a cooling or heating coil is installed or replaced. And last, if more than 40 feet of new or replacement ducts are installed in unconditioned space, any of these will be considered an altered space conditioning system and will need to be tested and meet the mandatory and prescriptive requirements.
Now, as far as the required HERS inspections, there are exceptions. So duct sealing is not required when any of the following conditions apply. So the system is not ducted. Obviously, there is no ducts to test, so there wouldn't be a duct test. There are less than 40 feet of ducts total, keep in mind, in unconditioned space, including the plenums and the FAU. The duct systems is sealed or insulated with asbestos, and there's obviously proof to show that. Or the system was previously tested and certified by a HERS rater and it can be documented through a CF3R or a 4R. This exception does not apply if more than 40 feet of ducts were added or replaced since the original verification. So if any of these conditions apply, duct sealing is not a requirement. And please keep in mind this is only applicable to altered space conditioning systems.
So an altered space conditioning system is going to be tested in the same way as a new system would be, with a couple of differences. So you're still going to perform the total duct leakage test exactly the same. You're going to perform the leakage to outside test exactly the same. The only differences that we see here is in the pass-fail criteria. So for an altered space conditioning system, when you're using that total duct leakage test, it's going to need to be less than 15%. If you're doing leakage to outside, it needs to be less than 10%. If you cannot achieve either of those values, then the contractor will seal all accessible leaks, and he'll identify those accessible leaks using the smoke test. And then you, as the HERS rater, you're going to visually verify using the smoke test again that there are no accessible leaks left to be sealed. When you use the smoke test, sampling is not allowed, and we'll talk about sampling in a different training module. Now the contractors do need to try and achieve option one first, try to hit that 15% total leakage. If they can't achieve that, then they can move on to doing the smoke test itself. Altered systems that have ducts or duct system components in the garage are going to be treated a little bit differently, and they're going to have different pass-fail criteria. So when you have new or replacement space conditioning ducts, air handling units, cooling or heating coils, or plenums located in a garage, then compliance with either items number 1 or 2 is required. So the first one is to perform a duct leakage test, and it needs to be less than or equal to 6% of the system air handler airflow, instead of the 15% that we saw on the previous slide. If you cannot achieve a 6% leakage rate, then you will need to go to the smoke test and have all accessible leaks located in the garage space to be sealed and verified through visual inspection and a smoke test by the certified HERS rater, which is you. So on a standard altered duct system where none of the ducts or duct system components are in the garage, you're going to have that 15% total leakage, 10% leakage to outside, or the smoke test. When you do have those components in the garage space, then you need to achieve either 6% total leakage or a smoke test. You cannot do leakage to outside when you have those ducts in the garage space. You do either a total leakage test of 6% or you'll do the smoke test if you can't achieve that 6% leakage rate. Now let's take a look at the various forms that are associated with duct leakage testing. So the main form for duct leakage is going to be the CF3R MEC 20H, and there are several variants of that MEC 20H that we'll take a look at. So the MEC 20A is going to be used for completely new duct systems. The MEC 20B is used when the low leakage ducts in conditioned space credit is taken. So this is a separate measure from just duct leakage itself, but a duct leakage test is required as part of that and will be documented on the MEC 20B. The MEC 20C will be used when the low leakage air handling unit measure is taken. Again, this is a separate measure from duct leakage, but it does require a duct leakage test to be performed, and so the 20C will be used to document the results for that low leakage air handling unit. The MEC 20D is used for complete replacement or altered duct systems. And then last we have the MEC 20E, which is for use when sealing accessible leaks using the smoke test for altered systems. So you got an altered system, you're doing the smoke test, that's going to be the MEC 20E.
And if you have any questions, as usual, feel free to contact us via messaging or email or give us a call.